Hello Year 12. So this is an introductory lesson to vectors. You can see I've already written here what exactly a vector is. It is essentially anything, any measurement with a magnitude and a direction, whereas what we call scalar only has a magnitude. So to put it into some context, some scalar examples would just be distance and speed, whereas our vector quantities would be displacement. Now you might think, what's the difference between displacement and distance? Well, displacement would say be 10 kilometers, but also have a direction of travel as well, whereas a distance would just be 10 kilometers. A speed as well might be 10 meters per second, whereas a velocity would be 10 meters per second with a direction as well, so west. Some other ones you will find are force. So some questions in your textbook have just given you a quantity like 10 newtons west and asked you, is it scalar or vector? And you can tell because that it's a vector because it's got both a magnitude and a direction. There's also momentum and acceleration as well that are vector quantities. So the symbol that we use to represent a vector is an arrow. So if I draw an arrow and I call that vector A with a little squiggly line, that is a vector because it's got a magnitude, so the length of the arrow, and a direction, the direction the arrow is pointing in. The example that we will do here is 80 kilometers an hour in northeast direction. So if I draw in my north and then I put in an arrow, please use a ruler. So I've drawn in my arrow using the tools here. I'll just put my north back in. That is going to be my 80 kilometers per hour vector. But then we're missing two things. We're missing what makes it northeasterly, and we're also missing a scale. So using your ruler, you might have done 1 kilometer per hour to 2 centimeters, 1 centimeter to 2 kilometers per hour. So you can see the length of the arrow is then proportional to the magnitude of the vector, and it's also got a direction. Moving on, different ways in which we can call name a vector is by putting a little arrow on top, bolding it, which you can't really do if you're handwriting, or putting a little squiggly line underneath. The thing with the arrow is we only do it in left to right. We don't ever write really the arrow from right to left, because the vector of AO wouldn't be OA with the arrow going in that direction. That's incorrect. If I wanted the vector AO, I would write it like that. The other thing is they've called this position vector and tide vector. They're pretty much the same thing. The vector which would be different to these two would be a free vector, which has no point A or B tying it. It would just be a vector which I can actually move around. So if I move it there, it's still vector A, move it here, it's still vector A, move it back to here, it's still vector A. Whereas these vectors here are tied by where the positions A and B are. So if A was the town Albury and B was Bulla, I can't actually, the vector from Albury to Bulla is set. I can't move the towns anywhere. That's why they're tied in position vectors. There's not much of a difference between the two. Now, the next part is the magnitude of a vector. The magnitude is expressed by using the absolute value sign or two vertical lines on either side of the vector. So when I refer to the magnitude of vector OA, we express it as OA with a line on either side, or just OA. So for vector A, we could have also done that, or that, or that. So that's essentially just referring to the length of the vector and not the direction. Another important feature is the tail and the head of the vector. So the tail is where it starts and the head is where the arrowhead is. Simple? Now, with geometric vector equality, it's essentially all of these vectors are the same because they have the same length and the same direction. So it's as if I copied and pasted it and moved it. I haven't enlarged it or rotated it or anything. It's straight copy and paste. So these are both parallel and equal in length. Now, geometric negative vectors are vectors with the same magnitude but in the opposite direction. So you can see it's as if I copied it and then flipped it and pasted it there. So I'm just going to erase this. We can write BA as the negative version of the AB vector. So geometrically negative vectors have same length, opposite direction. Excuse my messy handwriting. Now for that example, that's A, so copy and paste it, opposite direction, that's negative A. Done. I'm just going to add a little part here because it's going to make the next section easier. When we're adding vectors, we essentially, so say if we have vector A and we've got vector B, then vector A plus vector B is, so vector A plus vector B will be straight vector A, which I've copied and pasted, plus vector B, which I'll also copy and paste, but match up the tail to the head. Oh, that's not really a good match, is it? Right? Then my resultant vector, which is from my original tail to the final head, is A plus B. So the tips, the tails line up and the arrowheads line up as well. Now we're on to the next page. If you look at this parallelogram, it's made up of vectors A and B. They're asking for vector expressions for QP. So QP, you can see, is the negative vector of A. RQ is the negative vector of B. SR is going to be vector A. So I know SR is over here and A is over there, but you can pick up that vector and move it and it will still be the same vector. So in the same way, SP is negative B. Now, in this example of a bushwalker, we've got, I'll just give you a second, you can pause the video and read it first, but I'm just going to jump straight in. We've got my north, south, east, west. They are moving in that direction, east 30 degrees south for 2.8 kilometers, and then they're moving north for 4 kilometers directly. So they're asking, where's the position of the bushwalker? So they're essentially asking, what is this final vector, which I'll call X. Now in this triangle, you can see we've got 3 sides involved, but no angles. It's not a right angle triangle, so we should actually be looking at the non-right angled triangle equations. The sine rule is inappropriate because that needs 2 angles. We don't even have 1, so that's not the right one. So let's try the cos rule. The cos rule will require us to obtain a whole angle somewhere. Now we don't really have much to work with here, but if we look over here, I can construct another compass because that's in the north direction. These will be alternate angles, so that's 30 degrees, meaning this is 60 degrees. So using my cos rule, I'll have x squared equals to 4 squared plus 2.8 squared minus 2 times 4 times 2.8 cos 60. Now simplifying that and evaluating it in your calculator, you get 3.55528. Right? But because it's a vector, you also need to get the direction the bearing as well, so that, which I'll call theta. Now you can get that from obtaining this, which I'll call angle H, taking away 30, giving this angle, and then that angle take away from 90 will give you the bearing. So sine of H over 4 will give us sine of 60 over x, and rearranging it you'll get H equals 76.9961. Then if we minus 30 from it, H minus 30, and then take that away from 90, we'll get theta. So that actually gives us theta as 43.0039 degrees. Thus, all of this combined, the bushwalker is 3.56 kilometers north 43.0 degrees east, and that is all to 3 significant figures because the question didn't specify, and it's IB. Now in the next one we have A to C as vector A, but they've actually put the little arrow halfway through. That essentially, it means the same thing, so just don't get stumped by it. It's better practice to put the arrow at the end because it'll be easier for you to add and subtract and match up the vectors when you're adding them. So vector CA is going to be the negative of A. It's in the opposite direction. BC is this one, so that's going to be a negative B plus a positive A, because then it'll match up from tail to head. Negative B plus positive A. You can also write that as positive A plus negative B. In that last one, you only want the magnitude of what AB, so I'll just rub this out first, of AB plus BC, which will give you a final of AC. So that will just be the magnitude of vector A. Now that's different to if I just ask for the magnitude of AB and then the magnitude of BC. Well, the magnitude of AB is A, and the magnitude of BC in this equilateral triangle will also be A. So the answer would be 2A. So note the difference between the magnitude first and then added, whereas these are the vectors added and then the magnitude. So this next item bank question I've asked everyone to complete for homework. You can check the solutions on the OneNote. It is a really good question for you to do, and yes, you are allowed to have half vectors as a little hint. This is our last 2 pages before I end the video. With operations with vectors, you already know that you are going to join them from head to tail. So from A to B, you're going to have vector A there, you've got B there, so I'm trying really hard to try and make them identical to the original. And my final vector of A plus B will be here. Okay, you can complete the rest of that because it's very similar to what we've been doing. Now in this last part, these are kind of, you'll get used to it. So we'll just jump in. BC is going to be that vector, and then we've got plus CA will be over here. So my resultant vector will be from this to this, which is BA, not AB, because we have to go from the butt to the head. Now if we do BA plus AE plus EC, the answer will be BC. Now for the next one, we've got AB to BC and then to CA. So we've essentially gone from A back to A. That's an answer, or you can write the null vector 0. So that is the null vector. It hasn't really gone anywhere, but it's still a vector. And the answer to the last one, AB plus BC plus CD plus DE, will end up as from there A to E as that vector. Okay? Example 3, I'm quite confident you can do